which is a solution to Ambarzumyan problem on trees.
Thank you. I changed my title a little bit because I want to talk more. I would like to first thank the organizer for the invitation. These few days I've enjoyed very much the atmosphere here and listen to various experts and chatting with each other. And so anyway, and also yes, I put together a little bit of what I learned these few days into. I changed my transparency a little bit. So we are interested in a so-called metric graph or quantum graph, and so these are the conditions of the just one version. So it's a couple, and all right. So this my graph is this is my graph, and then the set of vertices and the set of edges, and contains with gamma I. I goes from 1 to n, okay, 1 to I, okay, and so I have the continuity. So I call V is a vertex in V. So I have a graph, and then this is one of the vertex. Of course, this can be more complicated, okay. So at every vertex, at every common interior vertex, we have the continuity, and we have the so-called Kirchhoff conditions at these vertices. And we have the Neumann boundary conditions. And so along the edges, this is the, you can call it, this is the Schrödinger operator. Our interest would be trying to recover, using the spectral data, using the eigenvalues, trying to recover this potential functions. And it seems to be a difficult task, as in the literature, not many papers appear. And so we start with maybe an easier job, the so-called Ambarzumyan problem. And so this is a joint work with E.G. Yanagida in Japan, and one part of it a joint work with Kovalchik from Ukraine. So this is a kind of an outline, and so the classical Ambarzumyan problem, 1929. In fact, is the set of spectrum n pi square can uniquely determine when the Q when you have a Neumann boundary condition, and this is the single instance that one set of eigenvalues can determine the potential function and on an interval. And for in case of spectral problems, Borg in '46 had long paper about he showed that essentially you can have, I mean, in general, one set of eigenvalues cannot uniquely determine the potential function. And in fact, in '87, Postrow and Trubowitz, using some Fourier series analysis, showed that there are infinitely many for the Dirichlet boundary condition. So in '97, Taiwanese mathematician Chen and Sheng they generalize the Ambarzumyan problem, the theorem, to the set of to the matrix Sturm-Liouville problem, Sturm-Liouville system, and so of course they consider the Neumann boundary conditions, and here we come in 2001. We found that for Dirichlet boundary conditions, if we add one condition on the potential function, then the set, this rho n, of course, is the square root of lambda n, can determine that Q is 0. This condition looks like a Fourier coefficient. So if the second Fourier coefficient of Q is 0, then all the other Fourier coefficients under this condition has to be pressed down, suppressed to 0. And recently, 3 mathematicians from China, they showed that for periodic boundary conditions, if we know that this rho n is 2n pi and multiplicity 2, then the potential function has to be 0. Of course, this is on a finite interval. And so in fact, this classical Ambarzumyan theorem, I would like to call it Ambarzumyan problems. There are, for different boundary conditions, they are distinct. And there are interesting results on them. So now guess on, consider the graph. So as I said, vertices and edges, this is the, I is the number of edges, and AI is the length of the gamma I in E. And so on the boundary, the derivative is 0. And here I have local, so-called local coordinate. I would like to use the local coordinates to denote the problem. It would be easier. And this local coordinate is kind of arbitrary. Once we set it up, it's the same no matter how you use it. And so coupled with continuity and Kirchhoff condition. And in 2004, Pivovarczyk showed that for the tree and then for the star graph, for the star graph, if you have a Neumann Ambarzumyan problem, if the Neumann boundary conditions, and then if the edges are the same, the length of the edges are the same, then the set of eigenvalues, you need to determine the potential function when consider the Q is 0, okay? And later on, Carlson and Pivovarczyk, they generalized the problem to a tree, and by analyzing very detailed analyzing at each vertex, step by step, and then integrate the result up and then solve it at the root. They show that when for the tree, if H has the same length, Neumann boundary condition, then this Ambarzumyan problem can be solved. So knowing that the edge, you can decompose an edge into 2 at the middle by looking at the midpoint as the as another vertex. So for trees with lengths in rational ratios, the same result is true. So this comes to our question: how about when the edges have irrational ratios? Now, this is the theorem that we want to talk about today. For the trees with irrational ratios, the eigenvalues are not very easy to compute. So our statement will be when we have arbitrary edge lengths, and then the set of eigenvalue or the spectrum of Q is the same as the spectrum when this potential function is 0, then Q has to be the 0 potential in L2. Now we have 3 key lemmas for to prove our theorem. First, we need to introduce the characteristic function. I shall give more details later on for this part. And so assume that when q is 0, then the continuity condition, and this is the initial value problem, and AI is a set of constants to be determined, and this is the Kirchhoff condition, then it has a solution in AI if this is invertible. And so setting the determinant will give us this kind of condition. Now, for simplicity, I would like to call it this is S1, C1, C2, C3, and S2, C1, C3, and so on. And so any row that can solve this equation is an eigenvalue. That's for sure. So for arbitrary Q, we have a similar formula, just like what we did, knowing that this C1, C2, C3 are no longer the simple cosine and sine, but they are very similar to cosine and sine by the theory of transformation operators, or by an initial value evaluation. So, this is the characteristic. We call it the characteristic function. Okay, and we found a method that this characteristic function, they for the tree, they can be decomposed. So suppose we have a tree. So we fix one point here. This point can be Neumann or Dirichlet, and then the other points are all Neumann. Then the corresponding characteristic function, I call it phi d, and then phi n and phi d, just by investigating this point at this boundary vertex, and we are able to cut it off. So we can decompose this graph into two, and then I call this edge 1, and the others maybe 2, 3, 4, 5, something like this. And then the most important will be 1. And this phi n, originally I call it phi n, but I change it into phi nk because we shall see will be equal to C1 phi tilde nk plus C1 prime phi d nk. So this tilde will be the characteristic function for this subgraph, and then we decompose it here. And for this one, phi d, it means that here, the smaller part, here at this vertex, we take on the Dirichlet boundary condition. So this phi d tilde is in fact this one. These all Neumanns, and this is Dirichlet. This is our phi d characteristic function. And but for the phi n, or phi nk, is different. It's the Neumann Kirchhoff. It's in fact the Kirchhoff boundary condition here, because you have this is an internal vertex for this subgraph, and so that's why we call it Neumann Kirchhoff, because sometimes it's Neumann, sometimes it's Kirchhoff, and this is the decomposition that we have. And on the other hand, if this is phi d, so this is a Dirichlet boundary condition, then we have this decomposition. Now C1 stands for the so-called C1x evaluate at A1. Okay, so it's called C1 for short. So this is the I shall prove this decomposition. I think it would be interesting to you. But let me use it. Okay. So for a caterpillar graph, I can decompose it one by one. First, sorry, this is a caterpillar graph. Okay. We have numeral edges, but this is the simplest caterpillar graph. Okay. And well, I will show you later this so-called the reduction formula. But I want to go on. After this decomposition, we can do things one by one by attaching or detaching one edge one at a time. And we have a computation that can help us to relate this. This is phi d will be. Let me go up. So phi d will be the at the specific vertex is Dirichlet condition, and then it starts with a Neumann, end on Dirichlet, and then phi nk will be starts on a new when you have one edge, so it starts in a Neumann and then end at a Neumann. So it's a cosine, something like cosine, and then at the end point you have a prime. And per psi, consider the Q naught be zero, the zero potential function. So it's cosine and negative sine. And using the transformation operator, one can relate this phi d with this psi d and then psi nk. So this is the Q potential function. This is the zero potential function. Then when rho is large, we have this kind of asymptotics. And similar, we can do the same thing for phi. And by an induction, we have this. We can relate the characteristic function for arbitrary Q when rho is large to the corresponding characteristic function for Q naught be zero. And so this is our actually is our second step. The third step, for a graph, the total length is an L, and AI is the sublength. Since it might not be irrational ratio, it might we can assume it to be irrational, and we want to approximate this irrational number with rational number. In fact, just now I saw in the talk of the previous lecture, there is some kind of decomposition like this. We are on the similar basis, okay? But what we want is we want that this sum for all I will be 1, and we want this kni and then mn to be a number such that the sum is preserved, okay? And using a pigeonhole argument, we have this kind of estimation. So we can approximate this irrational number by some rational numbers, and then this is the error. And using this approximation, we can have when mu n psi mu n will be 0, and but close to mu n we can compute this psi and then d psi d rho and so on, which means what? When rho is close to mu n, this psi will be very small. Okay, I think. Let me see. I think I made a mistake. Okay, this is phi. Okay, this is phi nk and phi d. This is the derivative of phi and then derivative of phi d. Okay, and all the points are rho. Okay, So what I'm saying is that at this mu n, phi mu n will be 0. I'm sorry. This is psi. This is psi, and near this mu n, we will have any row close to this mu n. This psi won't change a lot. Okay, and the change, the rate of change is negative n. So we can guarantee that. So it is something above or below 0, and we can with this constant, we can guarantee that the slope will be within this small interval. It will go to 0. That means what? Psi will have a 0 close to this mu n. I'm sorry, I'm mixing up. So this is phi. This has to be phi. Okay. So this is the story that I want to tell. This is the phi has a 0 close to the mu n, which are the zeros of the rational number. Yeah. And so using this, we can prove the theorem by first showing that the sum of the ki which appear in the formula is the sum of this potential is 0, and then knowing this one, we can check the 0 is the first eigenvalue. So we have well, for all Neumann boundary conditions, 0 has to be the first eigenvalue. So we put in the test term function, and then realize that 1 it will be the first eigenfunction, and so this is realized, and so Qi has to be 1. Okay, and so this ends the proof of this Ambarzumyan problem. Now, next I want to look at the decomposition. Okay, so this is phi. Here I'm looking at this problem again. At an arbitrary point, I can decompose it not even at any single vertex. I can decompose it here, and I can decompose it here. Okay, and any internal vertex. Now, for a tree, we can decompose. Now, so for a tree, we can decompose it into gamma 1 and gamma 2, and we define this phi. Right now, the boundary conditions, in fact, it can be arbitrary, and so I'm pointing up at this vertex. Okay, and I call phi nk if there is a Neumann or Kirchhoff boundary condition at this vertex, and I call phi d if there is Dirichlet boundary condition at this vertex, and so phi nk can be decomposed into. This is something like a product rule for the derivative, and so at this point, phi nk, I can decompose it into two graphs, and so it's the Neumann boundary conditions for this graph plus times the Dirichlet boundary condition for this graph, and the others are kept. The other, say, if it is Neumann at all ends, then these are Neumann. And this is Kirchhoff. Okay, and so it's the product of these two, And while for Dirichlet, if the phi d, we have Dirichlet boundary condition for this is the same as when all the others have Dirichlet. Notice that when we say this Dirichlet here, it means at all points is 0. So it's in fact further decomposed into smaller graphs. And so this is our theorem. And the theorem just now, what we have is, in fact, comes from the first one. What we have is the boundary is Neumann here. Is Dirichlet and Neumann. Okay. So this for this one. This the second is phi d. So is cosine. Okay, for the Neumann boundary condition. And this one and phi nk second will be this C1 prime. And the second formula runs out the same as from this A above, where this is D, Dirichlet boundary conditions. And we can use it, is the same as phi k here, because here the nk, we are emphasizing it on the vertex and not the boundary. So, and we can have this decomposition, where the first one is so-called phi d when you have Dirichlet, and this one is a function close to sine, and then the phi nk2 is a function close to sine, the derivative of sine. And so if this is true, then our corollary will be okay. Now, I try to illustrate this formula, especially the first one. Okay. I give an example. So suppose we have a caterpillar graph, and 1, 2, 3, 4, 5. Now I break it up into 2 here. So the solutions on each gamma I will be a linear combination of this Ci and Si. And then Ci will be 1 and 0, and Si will be 0 and 1 on this initial value. And because assuming this Neumann, okay, on this end, so the contribution from this Si term will be 0. And so we have considering this the continuity conditions, and this is the Kirchhoff condition, and so we can make it up into a matrix, okay, into a matrix. The so-called we call it a characteristic matrix. So it's C1 negative C2, C2 negative C2 negative S3, C3, and so on. All right, and so the matrix will be like this. Okay, so these two are the continuity condition, and this one will be the so-called the Kirchhoff condition at this end, at this vertex. All right, and so let me look at the previous one again. So 1 and 2, and then we have this one, C1 prime, C2 prime, C3 prime, S3 prime, and then yes, and this one will be 1, C4, C5 prime prime, and this one Kirchhoff, and at the other end will be continuity condition. So it makes up to a matrix like this. Okay, and so the characteristic function is the determinant of this matrix we define, and we can break it up into 2 matrices. Essentially, it's the product of this one. Okay, it's the product of this one. What other terms are left out is just this one, and then this C4 prime and C4 C5 prime. When you take this one, you can find out that you cannot you cannot say the result is just like you are reversing these two lines. Okay, I mean you cannot combine it with this one. You cannot have the alternating form is kind of a linear algebra. You cannot have this one on the n form, and so the result is like you have two big matrix whose determinants are multiplied, and then the other left out terms simply by reversing these two rows, and you can get the result. And this is what we have. So this is the big matrix, the left top and then right lower half, and the other matrix is a minus after you reverse it. Just you change this row with the other row, and so after you compute, it's the same, and then you look at this. This is the so-called phi 1 nk. It's the sorry, I'm not at a very good. So we break it up here. Okay. So this is the characteristic function for nk for this smaller graph is a star graph. Okay, and then this is the in fact it's a phi d of these two, and this one will be the phi nk, the phi d for the first one when we have sign when we have Dirichlet boundary condition up right here. So and then the smaller one will be the Neumann-Kirchhoff condition for the characteristic function. Okay, and we can multiply them out to have this characteristic function. So in general, the proof is like this. It's the same, and so I come to my conclusion. The formula works for arbitrary boundary conditions. When we have different boundary conditions, it might not be as simple. Just like this C1, there might be an S1 here, and so on. But the decomposition will be the same. And also, the complementary subgraphs, when we break it in two parts, these subgraphs, they may have loops. The loops are hidden inside the characteristic matrix. It doesn't change. I mean, our formula just come from a simple linear algebraic computation. And when we have so-called the delta type vertex conditions, things change in the when we have considering the Kirchhoff condition. But because of the nature of our computation, is again there's no difference. The formula still works. Thanks to John Harrison on Monday's talk, he talked about this Tessier work about, and then I get the paper out and then found that Tessier in 2008 had a similar decomposition formula, and his term is spectral decomposition, but I think it's just the same thing. It's the determinant of some matrix, and then his matrix. Well, I mean, it comes from some physical consideration, but I bet it's the same thing. So this is our formula. So on the whole, we kind of solved the Neumann and Ambarzumyan problem, and the formula, because we have some perturbation argument, so when the eigenvalues have multiplicity, it may not work. But for the tree and Neumann, things are good. Okay, and then we also have a reduction formula for the characteristic function. Thank you very much for your attention.